In this third video lesson on astrophysics and cosmology, we are going to classify stars according to two methods. The first method is going to be to classify stars according to temperature, and then the second method is going to be according to color or spectral classification. So as we've seen, stars have a range of properties. We've seen that some are hotter and emit most of their light in the blue region of the visible spectrum, whereas some are cooler and emit their light in the red region of the spectrum. Stars also have different masses. So for instance, lower mass stars like the Sun use the proton-proton cycle for fusion, while higher mass stars use the carbon-nitrogen-oxygen cycle in order to produce energy. We also see that some stars are bright and others are dim. So this all refers to the question about how do we go about classifying stars. What system do we use, or what systems do we use in order to make sense of the varying nature of stars that we encounter when we observe the universe? So obviously with classification, we look at particular properties that are similar in a particular group of stars. So we will look at all stars that are in a particular mass range or have a certain color or manifest some other property. So there are numerous ways of doing it, but generally the accepted methods are to group stars by their color and thereby their temperature. We've learned through Wien's displacement law that temperature and color, wavelength, hence frequency and color, are related. And then also by the composition of the elements in their atmospheres, and we know this through atomic and molecular spectra. So these are the two classification systems that we are going to look at, and they overlap greatly. So let's start off by classifying by color. So this table 1 here shows the spectral classes, colors, and approximate temperatures of the stars. And we've got the spectral classification according to O, B, A, F, G, K, and M. And we see that these spectral classifications are in relation to the color and to the temperature. So for instance, O, these stars have an electric blue color, which means that they have approximate temperatures greater, surface temperatures greater than 30,000 Kelvin. So these are super hot stars, up to 6 times or 5 times more hotter on their surface than the Sun. Then we have B, these are blue stars, and their surface temperature ranges from 10,000 to 30,000. So we can see that's quite a broad range of stars. We find what we call blue giants in the universe. We'll talk more about this later on, and they are very, very hot. We have A, these are white stars. They have an approximate temperature, surface temperature between 7,500 Kelvin to 10,000 Kelvin. We have things like white dwarfs that we find in the universe. They would fall into that class. Then we've got F, class F. They're yellow-white. They have a surface temperature that ranges between 6,000 and 7,500 Kelvin. We have G, which is yellow. That falls between 5,200 and 6,000 Kelvin, and our Sun falls in that range. Our Sun is classified as a yellow dwarf star. Then we've got K, which are slightly cooler stars. They have surface temperatures of 3,700 to 5,200 Kelvin. And they have an orangey color. And then last we have M on this table, that is, last on this table, M, which is a red color, and that's between 2,400 and 3,700 Kelvin for the surface temperature. So we have stars called red giants that fall in this spectral class. Now this classification scheme is known as the Harvard system, as it was developed at Harvard University in the early 20th century by Annie Jump Cannon, and it's based on an earlier scheme by an astronomer by the name of Draper. So we can use the following mnemonic to remember the order of classification. Only boring astronomers fight green killer Martians. Let's say that again. Only boring astronomers fight green killer Martians. So now, subsequent to this classification system coming into effect, Many new types of stars have been discovered, and some additional classes have been added to take account for these extended spectral types, so including the W spectral class, or Wolf-Rayet stars, which are hot blue emitting stars, and then the cool red and brown dwarf classes, the L, T, and Y classes. So this spectral classification based on temperature has grown subsequent to the early 20th century. So we now consider the second method of classifying stars by means of spectral class. So we've learned that stars continually fuse hydrogen into helium, and that stars with higher masses can form the other elements in the periodic table that are heavier than helium by continued fusion. So this means that different stars will have different atoms present in their atmospheres, depending on the mass and the type of fusion that takes place. So we've learned about the P&P cycle, which takes place in most stars, and then the CNO cycle, which takes place in heavier stars. So when light is generated by fusion in the core, whether it's by a P&P or whether it's by CNO cycle, these photons of light and electromagnetic radiation, they leave the very hot core in the center, and then they pass through the star to the cooler outer portions of the star. And most stars have an atmosphere above the surface of the star as well. So these photons of light and electromagnetic radiation have to pass through all of these layers before they leave the star and go out into space. Now, from our discussion on Wien's law, and remember we looked at black body radiation curves, all the frequencies and wavelengths of electromagnetic radiation are produced by a star, but obviously in different intensities, based also upon the temperature, the surface temperature. Now, when we look at the light that comes from a star like our sun, we expect to see a continuous spectrum, as is shown here, starting on the red side. So this would be infrared, red, orange, yellow, green, blue, indigo, violet, yeah, and then obviously ultraviolet. So because stars are plasmas, they're going to emit all the various frequencies of light. Now, when we look at the light from a star like our sun, we expect to see a continuous spectrum. And yet, when we do it, and we pass it through an instrument called a spectrograph, which is designed to split the light into its component colors and frequencies. It does it either by means of a glass prism or by means of something called a diffraction grating. We see that there are many, many dark lines to be found in the spectrum in most of the sections of the spectrum. So for instance, even in the infrared area of the spectrum, we see dark lines, some of them pretty significant. In the UV part of the spectrum, we see it. In the visible part of the electromagnetic spectrum, we see it. So this means that not all the photons of light and electromagnetic radiation have reached the spectroscope. And somewhere along the way between the sun and being observed, they've been lost. And that is why we have some of the wavelengths of light missing in what we call the spectrogram or the spectrograph. Now, the explanation for this was first given by someone by the name of Fraunhofer. Fraunhofer observed that there were lines missing in the continuous spectrum of the sun. And he linked this to elements being present, certain elements being present in the atmosphere of the sun, which were absorbing these specific wavelengths. So the outer layers of a star contain many different types of atoms, and the electron configuration for each type of atom is unique. So the electrons are separated by different energy levels at specific energies depending upon the nature of the atom, the type of atom. So if an incident photon has the right energy and corresponding wavelength and frequency, it may be absorbed by an electron in that particular atom and be moved to the appropriate energy level. So the electron gains the energy of the photon and is promoted to a higher energy level. But the original photon is now removed from the beam of electromagnetic radiation and has been absorbed by the atom. And so a dark line is formed at the corresponding wavelength in the spectrum. Remember, in essence, black is not a color, it's the absence of color. So many stars have the same composition, but the star's temperature affects the intensity of the absorption lines. So therefore the absorption spectrum can be used to classify a star. And in classifying, we are going to classify the star according to not only its temperature, but also its composition. So the classification system is arranged in order of temperature. So type O stars are the hottest, and the temperatures decrease such that the type M stars are the coolest. So we go from hottest stars at the top, hottest stars at the top, to the coolest stars at the bottom. So as you can see here in this figure, this is the typical spectra of the 7 main types of stars. Now, the 7 Harvard spectral classes can be further subdivided through numerals 0 to 9. So this means that an O0 star is the hottest type of O star, and O9 star is the coolest type of O star. Similarly, a K0 star is hotter than a K5 star, which is hotter than a K6 or a K7 star. So out of interest's sake, the Sun is classified as a G2 star. So we would see the spectrogram of the Sun would look roughly like this. Notice that with K stars and with M stars, there's a lot more absorption taking place because of the types of elements in these stars, and that's why you've got so much more black in the spectrograms of these stars. Let us now consider an example using the knowledge that we've just gained. So we have here that a star emits radiation that has its maximum intensity at a wavelength of 6,5 times 10 to the negative 7 meters. The A part of the question asks what is its surface temperature. So we've done problems like this before. The B part says state the spectral classification of the star according to the Harvard system. So lambda 0 is 6,5 times 10 to the negative 7 meters. That is the wavelength where the maximum intensity occurs for that particular star. So it's at the peak of the black body radiation curve. Using Wien's displacement law, lambda 0 multiplied by T equals 2,90 times 10 to the negative 3 Kelvin meters. Substituting for lambda 0, 6,5 times 10 to the negative 7 meters, we get that T equals 4,461,54 Kelvin for the surface temperature of the star. For the B part now, we're going to classify it. So we look and we say, okay, so according to the Harvard system, remember the Harvard system, we use the OBAFGKM system. And using the temperature of 4,461,54 Kelvin, which would fall in this range here, this range here between 3,700 and 5,200 Kelvin, we get to see that it would be orange in color, and so the type of star would be a K star. So now that we have learnt about two methods for classifying stars, we're going to move forward now in our journey to understand stars on a deeper level. So, for instance, we are going to look at a means by which we can graphically represent the types of stars and how they relate to stars, other types of stars. We're going to look at concepts and quantities like luminosity. We are also then going to look at different types of stars and the internal structures. So, for instance, dwarf stars like white dwarfs, we'll look at red giants, blue giants, and we will also refer to neutron stars, look at neutron stars, and then even black holes. So this is a fascinating topic, and one can really devote one's whole professional scientific career in studying astrophysics and cosmology. So this certainly is just an overview of this fascinating topic.